Okay, so I'm going to move on now and talk about another form of localization, and that is the localization at grain boundaries. Um, if you remember in the introduction, I said that my interest in localization came about because we had a problem in the reactor, CANDU reactors, Inconel spaces were seemingly cracking at lower loads and at a time when they shouldn't have been. And it seemed that could be attributed to helium, because at the end of life, these things are projected to have something like 30,000 atomic parts per million of helium, which is a lot. And that's a peculiarity of the CANDU reactor, because it's a very highly thermalized reactor, because it runs on natural uranium naturally. And so it needs a lot of thermal neutrons. Anyway, when this came up at the end of the 2000s, around 2009, assessment document was written by our engineering group, and they talked about slip interactions with grain boundaries, and that's why we were getting the intergranular failure, and with no evidence other than the fact that we were getting intergranular failure, and ignoring the fact that there were huge amounts of helium being generated. So, I mean, basically, two things then. One, I wanted to get to the bottom of it and either get them to pay attention to the helium, and the other thing was, if they were right, I had to find out a bit more about localization. So that's what I did, and I'm still in favor of helium embrittlement, I'm afraid. Okay, so here's an example of helium embrittlement, just from something from Fred Whiffen, Oak Ridge. So nickel alloys are particularly prone to helium embrittlement because they contain nickel. And nickel in a highly thermalized reactor will produce a lot of nickel 59 from the most abundant isotope, which is nickel 58. And nickel 59 is a very unusual isotope in that it has very high cross-section for helium production, as well as protons and hydrogen production as well, and then gamma reactions. So on all counts, getting nickel 59 produced is not good. Fortunately, it kind of saturates at around about 3% of the total, depending on the burn in and the burn out rate and what the spectrum is. So when we discovered we had a problem with spacers, Inconel X750 spacers, one of the reasons why I was particularly interested in it is because when I was just starting at ACL as a young person, I was given the job of doing a surveillance assessment for some flux detectors removed from a CANDU reactor. And it turns out that, ultimately, many years ago, flux detectors were exposed to the vault, to the moisture from the vault, and they realized that this was bad because you'd get nitric acid being produced with all the gamma radiation around, and early flux detectors in CANDU reactor designs were failing because of nitric acid attack. So then they encapsulated them in helium-filled tubes that went right through the reactor. But even then, after about 5 or 6 years, they would break, during startup, and ostensibly you could just replace them. But just by routine, there'd be a bit of a surveillance examination just to make sure it was nothing unusual. But it was unusual. These things were very brittle, and you couldn't attribute it to nitric acid attack. So that was my first introduction to the peculiarities of Inconel components. So in the CANDU reactor, it runs on natural uranium, has a very high thermal flux because of that, and therefore can operate and generate fission. And neutron economy is very important. So anything which is nickel or steel in the core, even though the calandria vessel itself is 3 or 4 stainless steel, anything in the core is minimized. The amount of mass in the core is minimized. Springs are tolerated because nickel alloys are good springs. And flux detectors are also tolerated because they can be taken out after a short while. They can be easily removed, but they'd only last for 5 or 6 years. At the edge of the core, there are these tensioning springs, and that's another story. They have some very interesting effects as well. So what I saw when I was young and I just started work at CNL was that being responsible now for the surveillance program of these flux detectors, because somebody died, it was very clear that there was something to do with the temperature. So basically they were encapsulated in a tube, a zirconium alloy tube, but obviously the helium gas was released at some point. It's funny, being helium, but also they just leaked out, replaced by air. Air is not as good a conductor, and these things got hot. And what you saw, that was they were very brittle. What I saw is they were very brittle in regions of the reactor where there was a lot of mass concentrated, a lot of temperature, and they corroded as well at the same time. So it turns out the corrosion layer was itself very odd. But the components which are outside of the rod, but also at the peak flux in the middle of the reactor, they were quite ductile. So there clearly wasn't, in that case, it seemed like it wasn't an irradiation effect. And if it was something synergistic with temperature, and clearly temperature was very dominant. So the implications were the material properties would stay good if it were operating at a high temperature. I mentioned there was a corrosion layer on these detector components where they were the Inconel 600 in this case, where they were hot, and it was a very high nitrogen layer, so you're reacting with the nitrogen in the air. And what was interesting is also this carbon layer mixed in there, and that comes from the transmutation of the nitrogen carbon. So one of the things that was clear is where the properties were bad, where these things were very brittle, there was this thick layer. And being naive and young, I said, well, okay, it's brittle where you have nitrogen layers. So we wrote a paper to do with the embrittlement due to nitriding. The idea was that the brittle layer would be would crack easily because it's can't deform, and you've got this high stress if you bend the thing in the outer fiber stress in this layer, and if the crack intersects with a grain boundary, it will then progress further. Again, this was a bit of a naivety, but didn't have much money to proceed further and do an in-depth study. Certainly didn't have the facilities to look into this in more detail, although I wanted to, but nobody was interested. So this relationship with cracking of components has been popping up quite a bit. It also happens in PWRs. Another Inconel 600 component, there was a report, operational experience report back in 2006, where a flux symbol was being pulled out of the Surrey reactor, and the report described it as it shattered into 6 pieces. Very interesting. Okay, so I just realized I've got a double there, but that doesn't necessarily mean anything. More recently, in the 2000s, people have been studying 316 stainless steel, and it was found in the 316 stainless steel tube. What was observed, this is a Fujimoto and Edwards, some work by Fujimoto and Edwards. They actually did do some TEM, and they were able to show that there were bubbles concentrated along grain boundaries, and corresponding with that, there was some embrittlement, some intergranular failure. Now, they're still kind of cautious about attributing that to helium, but they said it could be. So that was, but yeah, could be. At that time, this was the first instance where somebody had discovered or observed very small helium bubbles, certainly segregated at grain boundaries, in a helium environment. Bubbles in a PWR environment. So this is stainless steel. It's only 13%, 12%, 13% nickel. So you don't get an awful lot of helium. Plus it's a PWR spectrum, so it's not like CANDU, but enough to get this segregation. And people hadn't noticed it before in any other previous TEM studies of stainless steels. And Danny Edwards at the time kind of attributed this to the fact that people hadn't defocused the TEM. To me, that was kind of an odd thing to attribute the lack of observation to defocusing, because having spent tens of thousands of hours in an electron microscope, I know for a fact that you're defocusing and focusing and over-focusing left, right, and center whenever you're trying to find that focal point. So this should have been obvious in many cases. And then it became apparent to me, well, anyway, when you look at that, and then you look at other past observations, in this case, this is some work by Steve Brummer, and you look at the images that went with chromium depletion at grain boundaries, you have to be scratching your head and say, well, what is this? You know, what is this? You know, like it almost looks like you have a string of helium bubbles, just like the Danny Edwards case along the boundary. Doesn't look right. It looks like it's shifted somewhat, and the contrast is it's a peculiar. But that again, if you're familiar with electron microscopes, shifts in images and stuff like that, depending on the height and stuff like that, that's okay. You expect that, and the thing to do is to align the microscope well. So I mentioned that in the late 2000s, we had these problems with spacers, and what we were seeing was that when the spacers were removed from service, they were coming to the lab in bits. And when you put it all together, if a spacer, this is an Inconel coiled spacer, yeah, it gets damaged in transit, banged around, but you know, even though it's been irradiated, in this case it's about 1 dPa in this case, at that time that would be about 1 dPa, just a bit more. It's still ductile, but it's only after a very high irradiation or much longer time in the reactor it becomes very brittle. Take a piece of this in the cell, and just shows you how easy it is to break. So something is embrittling them, obviously helium. So when the material failed, I mentioned they failed along grain boundaries. So you had this classic intergranular failure of these spacers irradiated for a long time, and they would be ductile if it was unirradiated. So one can summarize the properties of these springs from results of crush tests. So their role, their function in the reactor is to hold up the fuel channel. So long as they can hold up and withstand the pressure from the fuel channel, that's okay, as long as they have enough load carrying capacity. But what we're seeing with, if you look at the unirradiated material, that this would be the load displacement curve. When it's irradiated to about 5-6 dPa, it goes up, the strength goes up, and the ductility drops a little bit, as you would expect. But with increasing dose, the strength goes down a lot. So this is an issue, and this is one of a big concern for the CANDU industry, because will it keep going down, or does it keep going down? The other interesting thing is that there's a temperature difference. So I mentioned that about the flux detectors. They had this apparent temperature dependence of the embrittlement, and it seems that was probably not nitride cracking, but really helium embrittlement. And what you see is that if it's a higher temperature, in the red here, it's worse. The embrittlement is worse compared to the lower temperature. Irradiation results in decreasing strength and ductility with increasing dose, and and once you get past a certain low dose, the degradation is just dropping, as you see here. So one of the things that I did as a program manager at Chalk River, I said, well, we must do some TEM. We didn't have any sophisticated fibs at the time, but we did have some electropolishing equipment. And we have very good technicians, and they were able to build a little twin jet electropolishing setup here to polish these 1 millimeter wide sections of the spacer. I mention this because I was in my office one day when the guys had prepared the samples, and they called me over because they said, what you thought you would see, we don't see it. So I had some young people just starting, didn't have any experience with the TEM, and they were quite mocking, basically, when I came over, and they said, you don't have the bubbles on the grain boundaries. So I said, let me sit down. So I spent half an hour aligning the microscope, and then produced these two images here. And basically, yeah, you've just got to align the microscope. So the difficulty and why people weren't seeing it in the past often, I think, is because you didn't have the microscope aligned. So one of those young chaps, or a couple of them actually, went away and published this later without giving any acknowledgement to the fact that I was the one who aligned the microscope for them and took the pictures. Anyway, why is this important? Well, it's important because if you have a material which is swelling like this, this is from a self-ion irradiation, ions, where you get lots of swelling for whatever reason. We don't have to understand why. Typically, the boundaries are bubble-free or cavity-free, void-free, I should say, and that's because vacancies are simply absorbed by the boundary, and then they can diffuse whatever they want or combine whatever. You don't get cavities segregate on the boundary when there's no helium there, but when there is helium there, you do. You get lots of segregation, and that is one of the features of helium. It gets to the boundary, and there it stabilizes any vacancies, which can also make it to the boundary, and you end up with this higher density of cavities, or bubbles in this case, low temperature. They're perforating the boundary when there's helium present. So cavities do not form the grain boundary in the absence of helium, but helium does stabilize the boundaries, bubbles on the boundary. Just a passing note that you knew this on. We commissioned a guy called Mike Demkowitz from TAMU to do some studies on this to see if he could simulate what would happen when we get an increased bubble coverage, because we wanted to know what the limit was. And Mike did some excellent work. And from that, he deduced that the fracture toughness dropped to almost, well, to zero by the time you get to about 30% coverage. But it's quite low and he deemed it at 18%. It's a point where the thing would fail. So what happens? Well, if you have a bubble-free material and you have a crack, for instance, in Mike's simulations, he showed that, basically the action of slip and a ductile crack is that, yeah, the crack can grow, but mostly outwards, and but it's also blunted, so you don't get this stress intensity here. You get an actual blunting of the crack, and that will tend to diminish any further advancements of the crack because you don't have a sharp edge here. However, in the case of bubbles, if you have a sharp crack and there's a bubble immediately in front of it, the dislocations can't go very far before they intersect the bubble. Eventually they'll slice off the bubble, but then you're creating a hinge arrangement here, and one can speculate, and perhaps this sort of thing is happening, and that's why you get that brittle failure when there's a lot of bubbles on the boundary. So one can hypothesize about how things progress if we look at the true stress, imagining hypothetically in the spaces, and a dose without defining what that dose is. Normally at zero dose, you have a certain yield strength and a certain ultimate tensile strength, and the grain boundary strength typically is much higher than either of these. So that when you deform, and even at low doses when the material's hardened, when you deform, it'll generally fail in a ductile manner, as it does in our spaces, even at low doses. But if you increase the dose, it might yield and then fails in a brittle manner. And ultimately, and this is where the million-dollar question, or billion-dollar question comes in, is what happens at very high dose? Does it just fail in a brittle manner? And it kind of looks like that. So the powers that be in Canada, I've worked at Connectrix, and we've been working on modeling to basically derive a model for the accumulation of bubbles on the boundary, and from that to build up a predictive capability for how long it would take before we get to that zero fracture toughness condition that Mike Demkowitz was able to establish. Use conventional rate theory expressions for the flux to the boundaries, and also take into account the pressure and the surface energy of bubbles. And ultimately, the principle is that you're always getting point defects of all types to the boundaries, and at low doses, there's not many bubbles in the matrix because you don't have enough helium generated to interact with this flux of point defects. And at high doses, this shuts down. So the good news is that from a point of view of the modeling, and from the point of view of the reactor operators, the rate is dropping with increasing time. So the modeling at least shows that it's not going to be an accelerating effect. in order to determine what does this mean, how do we model it, one could model the swelling in the matrix, and applying the same type of model, this is what the swelling would give for different reactors in different materials. I'm just putting this up just to illustrate that I've gone through the actual process of trying to model it. But this is for void swelling now, not for helium bubble production, which are two different things. So we've found that when you look at the measurements of the helium bubble production, you can deduce how the sink strength changes. And the temperature dependence, the sink strength in the matrix, it's actually decreasing with increasing temperature for a given amount of helium. It's smaller at the higher temperatures, and that's because the bubbles themselves are much bigger. And for various reasons, one then sees as a function of temperature, if we consider bubbles alone, we get an increase in the coverage with increasing temperature. But if we calculated the swelling, assuming a bias-driven growth of cavities, which is not the case, in fact, for our reactors, which are down at this temperature range, with increasing temperature, we'd actually see a decreasing coverage. And the cutoff is around about 350 to 400, so we arbitrarily put that in there, and that's when we get into the bias-driven growth regime. It comes in somewhere between 300 and 400 degrees C, depending on what one has for the cavity density, the dislocation density, the microstructure in general. Note also, in terms of coverage, if we had an EBR2 situation where there's very little helium, but there will always be some helium even in a fast reactor. But because of that, the balance tilts in favor of getting more coverage on the boundaries. So in EBR2, the coverage rapidly increases as we increase the temperature. That's in part because of having too little helium in the material. So it basically, you don't get a lot of swelling. The internal microstructure, basically the swelling drops off at a high enough temperature, whether you calculate it or whether you measure it. But there's still enough helium to get to the boundaries and cause you some problems. I'll finish just by talking about some other examples of helium embrittlement. I showed this earlier, the Inconel 718. Here we see that the 20 dPa Inconel 718 from Lance is very brittle, and that's related to the fact that you've got a lot of helium generated, likely. The one case I do like is with vanadium 15 CR 5Ti alloy. This is some work by Dave Bresky. I think it's Dave Bresky. And what he did is he looked at various combinations of DPA and helium at 500 degrees C, 520 degrees C. And what he found was that if you have a certain amount of helium, the material becomes brittle, and it basically fails intergranularly very easily, and that's because you have a high density of bubbles on the boundary. Basically, the failure is in the elastic region.